In the previous lecture, we related the quality of a linear programming relaxation to properties of the formulation. One thing in particular that we said is that if a linear programming relaxation has an ideal formulation, then the objective value of the linear programming relaxation is the same as the integer programming relaxation, and therefore it's good. In this lecture, we're going to take a completely different approach. We're going to identify and make rigorous the idea of a formulation being bad. Here we have pictured a bad formulation, or a bad linear programming relaxation. It's bad because when we draw the objective value of this linear program and we compare it to the objective value of our integer program, the distance between them is quite far away. This distance is really far. Because this distance is really far, this linear programming relaxation provides a very poor upper bound on the optimal solution of our integer program. To talk about how bad a linear programming relaxation can be, we need some measure of how bad it's going to be. And our measure is going to be called the integrality gap. The integrality gap is defined between an integer program and its linear programming relaxation. We know that because the integer program is a feasible solution to our linear program, that z star is going to be less than or equal to the optimal solution of our linear program. Now what we'd like to do is say or find some constant c such that when I multiply my integer programming solution by this constant c, it becomes an upper bound for our linear program. Let's go through this again. We know that an integer programming solution is going to be at most the value of our linear program, and what we'd like to do is find some constant c so that we flip this inequality. That is, we find some c so that now z star goes at least above our linear programming solution. This constant c is going to be our integrality gap. We'll see examples of integrality gaps in both the problems and the exercises that we do. An important point about the integrality gap is that this constant c is going to make this inequality hold for all instances of the problem. This constant c is defined for all instances, not just some instances. We'll work with integrality gaps quite a lot in the problems and the exercises, but we should understand why we've defined the integrality gap in this way. Specifically, why didn't we define it as some additive term? Let's suppose that instead we'd like to define the integrality gap as being some constant c so that when we add it to our integer programming optimal solution, we then become an upper bound to our linear programming solution for all instances. This might seem more natural. We're adding some number instead of multiplying the value of a solution. We'll go through a little proof of why this actually doesn't make any sense, and hopefully this will elucidate why we did a multiplicative factor. So let's suppose we pick an instance. And in this instance, we're going to solve our integer programming solution, and it's going to be equal to some objective value. We'll say that it's equal to the sum from I equals 1 to n of bi times xi star. Xi star is the optimal solution, the optimal variable values for our integer program. And we're going to compare this to the optimal solution that we get for our linear programming relaxation. And in our linear programming relaxation, we have the same objective value, the sum of the bi's, but in this case, when we solve the linear program, we have different variable values, LP, that are potentially real values, real numbers. And let's suppose that for this problem that we're solving, our integrality gap, defined in this additive way, is c. That means that if we sum from I equals 1 to n of bi xi star, and we add a constant c, that we're at least the value of our linear programming solution, the sum from I equals 1 to n of bi xi lp. What we can do is we can now take this instance and we can multiply it. So we're going to multiply this instance by some huge number that we're going to call capital M. and m is going to be huge. If we multiply our instance, the same integrality gap is going to hold. This integrality gap, this constant addition, is going to hold for all instances. In particular, it's going to hold for this large multiplied instance. So when we take the sum from I equals 1 to n of capital M times bi times xi star, and we add c, we're going to be at least the objective value of the LP for our multiplied instance, which is going to be capital M times bi of xi LP. What's interesting is that when we've multiplied this instance, we really haven't changed the actual variable values xi star and xi LP. These variables are actually going to be the same. And so this implies that if I take the sum from I equals 1 to n of bi xi star and divide everything by capital M, I get a valid inequality. So if I take this inequality and I divide everything by capital M, I get this new inequality. And now C over capital M, because M is large, this is very small. And because xi star and xi-LP in this multiplied instance, that is, these solutions, are the same as xi star and xi-LP in the original instance, I have some new integrality gap. Effectively, by multiplying my instance, I found some new, much smaller number that can work as my additive integrality gap. So this idea of defining the integrality as adding some constant to our integer programming solution isn't going to work. That's because, effectively, by multiplying instances, by having this ability to multiply instances, we can depress the value, the additive value, of this constancy. And this should bring an important point. Whenever we have an integer programming solution and compare it to a linear programming solution, the important thing isn't how far away they are in an additive sense, but how far away they are in a multiplicative sense. In some ways, this additive factor, this plus c, isn't going to matter. It's only the constant multipliers in front of z star that are going to matter.